Welcome to the Curious Machine. Today we're diving deep into a number that has, well, it's really captivated humanity for thousands of years. You might have heard it called the divine proportion, maybe the golden number. It's this concept that seems to pop up everywhere, from ancient geometry all the way to modern art. We are talking about the golden ratio.
That's right. And our mission today for this deep dive is really to unpack what the golden ratio actually is. Where does it come from? Why do people think it's so special? But maybe most importantly, we're going to try and separate the facts from the fascinating fictions that have kind of grown up around it, especially when people talk about seeing it in nature or, the universe.
Yeah, because honestly, getting a handle on this concept offers you a real shortcut to being, well, pretty well informed about an idea that you hear everywhere, but it's also, let's face it, very often misunderstood. So yeah, let's unpack this thing.
Absolutely. Let's start with the basics then. The golden ratio, it's usually represented by the Greek letter phi, that's phi, and its value is approximately 1.61803398887, and it just keeps going.
All right, so it's like pi in that way. It's an irrational number. The decimal goes on forever, never repeats. This seems pretty unique for something that's supposed to be about perfect proportion. How do we actually, calculate it or define it?
Well, there are a couple of main ways. Geometrically is maybe the classic way. Imagine you have a line segment, right? And you divide it into two parts, a longer part and a shorter part. If the ratio of the whole line's length to the longer part is exactly the same as the ratio of the longer part to the shorter part, then that ratio is the golden ratio, phi.
Okay, wait. So the whole line compared to the big piece has the same relationship as the big piece compared to the little piece.
Exactly. So if the parts are A long and B short, it's A plus B divided by A equals A divided by B. And both those equal phi, about 1.618.
Okay, that makes sense. It's all about that specific proportional relationship. No wonder they called it the divine proportion. But you mentioned another way, something arithmetic. How does a sequence of numbers get you there?
Yes. That involves Leonardo Fibonacci and his very famous number sequence. You know the one, 0, 1, 1, 2, 3, 5, 8, 13, and it just keeps going. Each number is just the sum of the two before it.
Right, the Fibonacci sequence. Pretty simple pattern.
Deceptively simple. Because if you start taking the ratio of successive numbers in that sequence, like say 8 divided by 5, that's 1.6. Then do the next pair, 13 divided by 8, that's 1.625. Keep going. And the result gets closer and closer and closer to phi, to that 1.618 number. It's this amazing convergence.
Wow. So Fibonacci stumbled onto the sequence, but he didn't connect it to phi himself.
Apparently not. He was interested in, rabbit populations originally. It was later mathematicians, people like Simon Jacob in the 1500s, and then Johannes Kepler in the early 1600s, who really rediscovered that link between the sequence and the ratio.
So this number, phi, has been hanging around for ages, popping up in different contexts.
Yeah.
What's its sort of historical journey been like?
Oh, it has a really rich history. Goes way back. Ancient Greek mathematicians were definitely studying it. Euclid, around 300 BC, he formally defined it. He called it the extreme and mean ratio.
Extreme and mean ratio.
But there's maybe an even earlier and frankly more dramatic story involving Hippasus. He was a follower of Pythagoras back in the 5th century BC. The story goes that Hippasus discovered that the golden ratio, and also the square root of 2, were irrational numbers. They couldn't be written as simple fractions.
And that was a big problem.
A huge problem for the Pythagoreans. Their whole philosophy was built around the idea that, whole numbers and their ratios govern the universe. Everything was rational, neat. Discovering irrational numbers was like finding a fundamental flaw in the code of reality to them. It was so controversial that some stories say Hippasus was actually thrown overboard from a boat and drowned for revealing the secret.
Whoa. Okay, that's taking mathematical disagreements to a whole new level. High stakes indeed.
It really shows how deeply they felt about numbers and cosmic order back then. Anyway, fast forward a couple thousand years to the Renaissance, and figures this big resurgence. You have Luca Pacioli writing a book in 1509 called Divina Proportione, the divine proportion, and guess who illustrated it?
Let me guess, Leonardo da Vinci.
You got it! Da Vinci did the illustrations. Pacioli's book really explored the ratio's properties, its geometry, and tied it to spiritual significance. That's really where the divine proportion nickname solidified. And Kepler, who we mentioned linked it to Fibonacci, he had this great quote. He called Pythagoras' theorem a nugget of gold, but the golden ratio, he called it a precious jewel.
A precious jewel. It's amazing how it keeps capturing people's imagination across centuries.
Yeah.
What do you think is behind that persistent fascination, even when, the divine stuff gets debated?
That is a great question. I think part of it is its sheer mathematical elegance and maybe how it keeps appearing in unexpected places, even in modern science, like Roger Penrose's work on non-repeating tilings, these amazing patterns that cover a surface without ever repeating perfectly. They're often built using shapes based on phi.
Penrose tiles, right. Fascinating stuff.
And then there was the discovery of quasicrystals by Dan Shetman in the 80s. He won a Nobel Prize for it. These are materials where the atoms are arranged in an ordered way, but it's not a repeating periodic pattern like normal crystals. And guess what symmetry they found?
Let me guess. Related to phi.
Bingo. Symmetry is linked directly to the golden ratio. It really does suggest some kind of deep mathematical order woven into the fabric of things, even if it's not quite divine in the old sense.
Okay, so we've got the math, the history, these intriguing modern connections. Let's shift gears a bit. What about when humans intentionally use it? This is where it's less about finding it and more about, designing with it, right?
Precisely. And when humans decide to use the golden ratio, you can definitely find clear examples. Architecture is a big one. Le Corbusier, the famous Swiss architect, he was a huge proponent. He developed this whole system called the modular, which was based explicitly on the golden ratio and human proportions. He really believed it created aesthetically pleasing, harmonious spaces.
Did he use it in actual buildings?
Oh, absolutely. His Villa Stein, for example, has lots of elements, windows, room dimensions that are designed to approximate golden rectangles. Another Swiss architect, Mario Botta, is also known for using it deliberately in his designs.
And outside of buildings, what about art? You mentioned Da Vinci illustrating that book, but did artists consciously use it in their paintings?
Sometimes, yes, very explicitly. Salvador Dalí is a great example. His painting, The Sacrament of the Last Supper, is a really clear case. The canvas itself is dimensioned as a golden rectangle. And maybe even more strikingly, he painted this huge, transparent dodecahedron that's a 12-sided shape strongly linked mathematically to phi floating right above Jesus and the table. There's no doubt he intended that connection.
Right, that's pretty unambiguous.
I see.
Dalí was definitely making a statement there. Where else do we see this kind of deliberate application?
Well, you find it in all sorts of design elements, sometimes subtly. Things like the flag of Togo, apparently, certain classic book page layouts, playing cards, postcards, even things like widescreen television ratios are often close to it. And people talk about it in music, too. Composers like Eric Satie and maybe Claude Debussy are said to have structured certain pieces around its proportions, dividing sections according to the ratio.
Interesting. So beyond just looking nice, does phi have any practical sort of optimization uses in science or engineering?
Yes, it does actually. It pops up in some optimization problems. For instance, arranging mirrors on a satellite called Starshine 3. They used points based on the golden ratio on a sphere to get the most even distribution for reflecting sunlight. And in math and computer science, there's an algorithm called the golden section search. It's a really efficient way to find the minimum or maximum point of a function if you know it has only one peak or valley in a certain range. So yeah, it's got real-world practical applications too, not just aesthetics.
Okay, so we've covered the math, the history, the times. Humans clearly did use it in art, architecture, even satellites. Now, let's pivot to maybe the most contentious area. The claims about finding the golden ratio just scattered throughout nature. This is where things get a bit fuzzy, right? What's the first thing we need to keep in mind when we hear these claims?
That's a really crucial point. When we start looking for feel in nature, the first big lens we need to apply is, honestly, human psychology. Our own perception and cognitive biases. We're pattern-seeking creatures, right? And if you go out looking for a specific number, like 1.618, your brain is primed to find things that seem to fit, even if they're just close approximations. It's that seek and you shall find effect.
So we might be seeing what we expect to see.
Exactly. And tied right into that is the question, what counts as close enough? Remember, feel is a very precise irrational number. 1.6180339 and so on. Natural things, biological systems, shells, whatever, they're rarely that precise. They have variations. So if someone measures something and gets, say, 1.6, 1.7, or maybe even 1.5, and they say, look, it's the golden ratio. Well, is it? How close do you have to be? If you relax the definition too much, you could probably find feel-like ratios everywhere, which kind of makes it meaningless, doesn't it?
Yeah, that dilutes the whole idea. Okay, so keeping that bias and the close enough problem in mind, let's tackle some specific examples people always bring up. What about the human body? You hear claims about arm bone ratios or height to navel height.
Right, those are super common claims. But when scientists actually do large-scale measurements on lots of different people, they find a huge amount of variation. Average ratios might sometimes land vaguely near 1.6, but individuals vary widely, and very few people actually match the golden ratio precisely in those proportions. Our bodies are beautifully proportioned in many ways, but not rigidly built to phi.
Okay, so the body stuff is mostly out. What about the absolute classic, the poster child? The nautilus shell. That spiral looks so perfect.
Ugh, a nautilus. It's probably the most persistent myth and a perfect example of that close enough issue and just misidentification. Nautilus shells do grow in a spiral pattern. It's called a logarithmic spiral, which is a very common growth pattern in nature, where the size increases by a consistent factor over a term. But, and this is the key, when people carefully measure the expansion rate of actual nautilus shells, it's consistently not the golden ratio. The ratio is usually somewhere between 1.2 and 1.4 per quarter turn, not the 1.618 required for a true golden spiral. So yes, it's a logarithmic spiral, but no, it's not the golden spiral. People confuse the general type with the very specific one.
Okay, that's a big one debunked. What about other spirals in nature? Pine cones, sunflowers, pineapples. You definitely see spirals there.
You absolutely do see spirals, and that's where the Fibonacci numbers often come back in. If you count the number of spirals going clockwise and counterclockwise on a pine cone or in the seed head of a sunflower, you very often find two adjacent Fibonacci numbers like 5 and 8, or 8 and 13, or 21 and 34.
Ah, okay. And the ratio of those numbers gets close to phi, as we said earlier.
Exactly. So these plants display patterns related to Fibonacci numbers, and the ratio approximates the golden ratio. But it's usually an approximation, not a dead-on perfect phi. The universe isn't like meticulously engineering every pinecone scale to be exactly 1.618 times the size of the previous one. It's using a packing system related to Fibonacci numbers, which tends towards phi.
Okay, that makes sense. It's related, but not identical. What about the claims I've heard about DNA itself, like the dimensions of the double helix?
Yeah, that's another one that gets repeated a lot, but it doesn't hold up to the actual measurements. The claim is usually that one full turn of the DNA helix is 34 angstroms long, and the width is 21 angstroms. And look, 34 and 21 are Fibonacci numbers. Their ratio is close to phi, but the real measurements are more like 34.86 angstroms for the length of a turn and about 20 angstroms for the width. The ratio there is closer to 1.74, which is, not 1.618. So, nope, DNA doesn't fit either.
And what about huge structures? The Great Pyramid of Giza, the Parthenon in Athens. So many books and shows claim they're built on the golden ratio.
Those are also really widespread myths, but again, not supported by solid historical or architectural evidence. Most credible scholars and Egyptologists agree the pyramids were likely designed using simpler, whole number ratios based on measuring techniques they actually had, like using seeped units for slope, which leads to ratios like 14:11, not phi. For the Parthenon, detailed analysis shows it was probably designed using ratios like 4.9 for its basic proportions, again, simple integer ratios common in Greek architecture. The idea that phi is perfectly encoded often relies on, selective measuring points or drawing lines where they weren't necessarily intended.
So finding a ratio close to 1.6 somewhere in a complex building doesn't mean the whole thing was designed around phi.
Exactly. It's easy to find approximations if you look hard enough. And the same goes for claims about artists like Leonardo da Vinci using it secretly in the Mona Lisa, or Vitruvian Man, or Pete Mondrian in his abstract grids. There's usually no mention of it in their own notes, and precise measurements often don't support the claims rigorously.
Okay, so if all these specific examples are often shaky, disputed, or just approximations, why do we sometimes see patterns in nature that seem related to physics or Fibonacci numbers like in those plant spirals? If it's not some mystical code, what's the actual scientific reason?
That's the really interesting part, and it comes down to physics and evolutionary efficiency. Take leaf arrangements on a stem or seeds in a sunflower head. Plants need to pack things efficiently, right? Leaves need maximum sun exposure without shading each other too much. Seeds need to be packed tightly. It turns out that arranging elements using an angle related to the golden ratio, called the golden angle, which is about 137.5 degrees, provides the most efficient packing and the least overlap over time as the plant grows.
The golden angle related to phys.
Yes, mathematically it's derived from phi. It's 360 degrees divided by phi squared, roughly. Using this irrational angle means that as new leaves or seeds form, they never line up exactly above previous ones. They always fall into the biggest gap. And phi is special here because, in a mathematical sense, it's considered the most irrational number. It's the hardest number to approximate well with simple fractions. This property makes it uniquely good for creating these highly efficient, non-repeating packing patterns.
So it's not about the number 1.618 itself being magical. It's about the properties of that irrational number leading to efficient physical arrangements through evolution.
Precisely. It's about evolutionary optimization, finding elegant mathematical solutions for practical problems like light exposure and seed packing. Nature utilizes efficient mathematical principles, and phi happens to be particularly good for some of those. It's physics and biology, not necessarily a hidden message.
That makes a lot more sense. It grounds it in something real and observable. So reflecting on all this, what do you find most compelling about this whole golden ratio story? This duality between how humans use it versus how it actually appears or doesn't in nature.
What I find really compelling is how it serves as a kind of mirror to ourselves. We humans clearly find something beautiful and ordered in this ratio, enough to consciously embed it in our art and architecture, seeking harmony. That's real. But when we project that onto nature, things get more complex. Nature uses mathematical principles, including ones related to phi, for efficiency and survival. But it's not writing us messages in code, it's optimizing. The story in nature is more about elegant solutions driven by evolution and physics, rather than a deliberate application of a divine proportion. It forces us to be careful about interpreting patterns.
That's a really powerful distinction. The golden ratio ends up being this fascinating reminder, doesn't it? That math gives us incredible tools to understand the universe, but real understanding comes from critical thinking, rigorous observation, tested ideas, not just from wanting to find mystical patterns everywhere. It makes you wonder, what other hidden truths might we be missing because we're too focused on these captivating, but maybe ultimately unsupported beliefs? Definitely something to think about.
Thank you very much for sharing this enjoyable conversation with us. Until we meet again tomorrow with a brand new topic, take very good care of yourselves. Goodbye.